Okay, so this is question 6 now. We're looking at fission. What is fission? Oops. What is fission? Fission is splitting a nucleus. So splitting a nucleus into two, which is what's happening here. We've got the uranium nucleus, and it's been separated, split into two other nuclei. We call these two nuclei that have been split up daughter nuclei. So these are daughter nuclei. Daughter nuclei. And the one that was that has been split, we call the parent nucleus. These little things here, these are very. Let's make sure that's pointing at the right one. These things here, which I'm going to label in a different color. These are other neutrons. This is a neutron here, and in fact it must be slow moving. I'm just going to put slow neutron. And these are daughter neutrons. Okay, daughter neutrons. So I imagine I might have answered some of these questions now. Let's have a look. During the process of nuclear fission, a uranium something absorbs. Okay, so it's going to be a uranium nucleus absorbs a neutron. Okay, this one I haven't answered above, but it's electromagnetic radiation is released in the form of gamma rays. So gamma rays are, they're a type of nuclear radiation, and it's released in many different ways, but one of the ways is in fission. Okay, so the UK needs at least 25 million kilowatts of electrical power any time a nuclear power station has. Calculate how many nuclear power stations are needed to provide 25 million kilowatts of nuclear of electrical power. So this question is really just testing how baffled you get with large numbers. If we're and they do stress people out because, well, you don't normally come across such big numbers in everyday life. So let's have a think about it carefully. We need that much money, that much energy, and we have this much energy. So in other words, each power station produces that much the energy in green. Calculate how much would be, and that number at the bottom is just simply again the amount that we need. So if we need that much, and each one gives us, if we need this and each one will give us that, then to work out if we want to know how many lots of this would go into that, well, that's divide then. So 25 million into 2,400. Well, you can do this. I mean, you're allowed a calculator in GCSE physics anyway, and in fact A-level physics anytime. You're not allowed calculators in maths papers. So I'm going to do the sum on the calculator, but then I'm going to show you a trick with these. Even if you are allowed a calculator, it's still worth doing some of these things in your head as well. So that's the sum, and sure enough, it gives you 10.4, which is well. So you can, okay. It's asking us how many power stations. Now you can't say that you would need 10.4 power stations, can you? Because you can't have 0.4 for power station. Now, the mistake some people might fall into is rounding it down, because the closest number to 10.4 is 10. but 10 power stations wouldn't provide enough energy, would it? Because we would need 10.4. So you actually round it up in this case. It's a bit confusing. So the correct number is 11 power stations. I was going to talk about the trick for these numbers. So sometimes when you're, especially that one wasn't too complicated, but or too long, but sometimes these calculations you can end up making a mistake on your calculator, and it's worthwhile if you get a chance to do some of this in your head. So I think what we can do here is we can say, well, first of all, let's cross off 3 zeros at the top there, 3 zeros at the bottom there, and then we'll cross off 2 zeros there and 2 zeros there. And we can say that 24 is roughly the same as 25. So roughly we're expecting an answer around about 10, because we're talking about 250. It's around about 250 divided by around about 25, which would be 10. So so you have to sort of do some of these calculations in your head sometimes. I mean, you could just do it in the calculator and I got the right answer, but if I'd done something wrong, but I had done that sum in my head, then I would be able to get an idea of whether or not I'd done it right. Maybe in that particular calculation, it's not necessary to do that because it's just going to take too long. But in some calculations, it really is a good idea. Okay, what else do we have? So this is still question 6. Yes. So state 2 environmental issues caused by generating electricity using nuclear power stations. Do not put global warming. Nuclear power does not cause global warming. Why? Because you're not burning. The fission reaction we looked at a moment ago, that isn't burning. It doesn't produce carbon dioxide. So that's not an issue. There are issues though. And one of the issues is, essentially it's mainly around nuclear waste. There's lots of other things you could say. I'll just briefly show you what you could say, and I'll add that to this whiteboard. And if you've got this package, well, that's huge. Let's shrink that down. Oh, I like the fact it's at an angle. Doesn't that look kind of cool? Maybe. Let's just make it a little bit bigger though. So, no, let's not do it. That's an angle. Okay, so like I said, it's around the waste really, because once you've used these nuclear fuel rods up and you've collected the energy from it and heated up the water and produced electricity, you have the waste product, which is actually radioactive, and that can be quite dangerous, right? So what do you do with it? Well, the trouble is it's radioactive for, in some cases, thousands of years. So storing it is a real issue. So you could have said anything along that. I mean, I could talk for some length and write a paragraph, which would get loads of marks, but we're only looking for 2 marks. So it's radioactive, it's toxic, it needs to be buried, any of those things, any 2 from that. And this bit on the right, that's just what it also allows. Okay. As I said, I'm not going to go too much into these details because this is really a work solution video I'm doing here. If you want me to produce a video on a particular topic, then just let me know and I can make I can focus on one of these many topics I'm brushing over right now. So the UK the UK currently generates a lot of electricity by burning natural gas. This process releases carbon dioxide into the atmosphere, shows the carbon dioxide changing over the 115 years. Okay, so it looks like the questions on the next page. Right, okay, this is frustrating, isn't it? One of these cases where you're going to keep flipping back and forth. So, all right, well, it's not too hard to see. I mean, one goes up, one goes down. Sorry, what, they both go up, I mean. Give one similarity and one difference. Well, I think it's the similarity is easy to spot, isn't it? They both go up. It's not good to say they go up, though, is it really? I mean, you can probably say they both increase, and you get the mark. I can just double check that. Yes, they both increased. I think it'd better to say they both increase as time goes on, but yeah, that's fine though. They both increase. The difference is this bit here. Can you notice it levels off? It starts to level off here. So the global temperature is starting to level off, whereas in this graph, the carbon dioxide is still increasing. Now, what does that mean? I mean, this could get into a massive political debate here. My standpoint on this is that humans are definitely causing global warming, and we need to get our act together. So I don't really like the idea. Don't really like this question. There's a lot of different data out there that would suggest different things. So, but in answering the question, the similarity is they both increase. The difference is the temperature is leveling off. Temperature levels off. Okay, this is another example, one of those questions you don't really need to know anything about global warming. You just need to be able to read the graph. And there's a lesson there that if you see a question, you think, oh, I don't know anything about that topic, or I'm weak in that topic, don't necessarily let that put you off.